Hello everyone, welcome to Helm of Science. So in the last class we had talked about the introduction to the chapter coordination chemistry, wherein we discussed about why the chapter is important, why we are discussing about coordination chemistry, what makes it so important, and of course we learned about the bond, which is a coordinate bond, and how it is formed or the process to form it, right? In today's class, we are going to talk about the syllabus part of the chapter, which is important as far as our board exams are concerned. So let's begin. In order to form a coordinate bond, what was important was we needed few things for the bond to take place. Number one being a metal, right? So we need a metal for sure. And we need is a ligand. Now, what do I mean by a metal and what do I mean by a ligand is what we are going to discuss right now. So, the first thing we need is a metal, and the second thing we need is a ligand. Now, why is metal important? Usually, metals are substances which are electron acceptors or electron deficient species. Metals are electron deficient species. If I would use a more technical term, then I would say that metals are referred to as Lewis acids. Lewis acids are acids which are not only electron deficient, but they also accept electron pairs. Right? Now, why metals have been chosen and not a non-metal? The reason being, metals can easily achieve their octet configuration. Metals can easily achieve octet configuration, which is why metals have been chosen to be the central species during the formation of a coordinate bond. The second thing which we require is ligand. Now, ligand is a substance rather which donates electron. All right. So, how is it supposed to donate? Ligands are species, those that donate electrons. So we can write it as that they are electron rich, right? Now, what is its function? Its function is it will donate its electrons because or so as to help the metals achieve their octet configuration, or rather, since the metals are the electron deficient species, the ligands will help to stabilize it or create a bond by donating its electrons. Now, there might be a question that what do I call as ligands, or what kind of species do I call as ligands, right? Suppose there is chlorine and Cl minus. Now, which one is a ligand and which one is not a ligand? See, chlorine in its elemental state has 17 electrons because its atomic number is 17. So, it has an incomplete octet, right? Whereas Cl minus has a complete octet, right? So it will, and also it has an excess of electron. So it will be able to donate its electron and behave as a ligand in this case. So Cl minus is a ligand, Cl is not a ligand. Clear? Okay. Now, how would we draw a coordination compound? Suppose a compound mentioned to us is CONH3 whole 3 Cl3. This is the coordination compound given. Now, how do I know this is a coordination compound? Because coordination compounds are made up of two things. One is this third bracket symbolizes a coordination sphere, which means that the portion mentioned inside this part is the coordination compound. Right? Now, we have electron donating species like Cl and ammonia, which donates its electrons via the lone pair in case of ammonia to a metal that is cobalt. Now, first things first, we need to find out the charge of the metal before we proceed to draw the structure, right? So, firstly, how would we find out the charge on the metal? Now, the charge on the metal is referred to as primary valency. Primary valency, which actually gives the charge on the metal, or more precisely known as the oxidation state of the metal. Okay, that is what is referred to as a primary valency. And there is another valency which is used, that is a secondary valency, which we shall discuss later on. But just for the definition's sake, we might write it down here. That is, secondary valency refers to the coordination number of a metal. Right? Okay. What is a coordination number? That also we'll discuss later. Right? So we have one primary valency and one secondary valency. Now, the thing is, we have to find out the primary valency of the metal, that is the oxidation state of the metal. Since it's unknown to us, let us consider a variable x for its oxidation state. Now, Cl is a 1 electron donating species. So 3Cl would make it minus 3 electron donating species. Ammonia is a gas, right? So since ammonia is a gas, so we can write it down as that it donates, or the charge donated by it is 0, because gases do not donate charges, right? So the entire value of the coordination sphere would be 0. Why? Because there is no charge mentioned on the coordination sphere. So the entire value would sum up to 0. So what do we get? X is equal to plus 3. So the charge of the oxidation state on cobalt is plus 3. Okay. So now you might ask me, ma'am, how do we know which is a ligand which donates electrons, or which donates 1 electron, 2 electron, or does not donate any electron? How do we understand that way? So for that, we need to understand few things. That is, ligands are of various types, right? So ligands are of various types. But primarily the ones which we use in our 11-12 syllabus is monodentate ligands, bidentate ligands, neutral ligands, and of course we use one more thing which is little common in this case, are chelating ligands. Chelating ligands. These are the 4 classification of ligands which we generally use in our syllabus. Right? Now before proceeding, we need to know that this word dentate here, what does dentate mean? Now dentate originates from the word denticity. Denticity. Now what is denticity? Denticity is actually teething. Teething. Now what do you mean by that? Denticity means the number of tooth or the number of teeth a particular ligand has. Supposing I say Cl minus. So this minus charge behaves like a ligand, or this minus charge donates electron density to the metal. Since this minus charge is donating an electron density, we refer to it as a tooth of the ligand, which actually kind of bites the metal atom. By donating the electron density to any metal M, it actually supposedly bites the metal atom just like we bite any food using our teeth, right? So that is what is denticity, the tendency to bite a metal atom, which in terms of chemistry we see that is donation of electrons to the metal atom. Now mono refers to as single or unimolecular, 1. Bidentate refers to as 2. So, which means that any ligand which can donate one electron is referred to as monodentate. So, Cl minus donating one electron is referred to as monodentate ligand. Whereas, if I use supposedly SO4 2 minus, SO4 2 minus behaves as a bidentate ligand because it can donate 2 electrons simultaneously. Then we come to neutral ligands. Neutral ligands are ligands which do not donate electron density, right? Or I won't say it does not donate electron density. It does, but it does not donate electron density in terms of charges like Cl minus or SO4 2 minus. So neutral ligands example would be ammonia because it is a neutral species. It's a gas, so it cannot donate electrons in the form of charges. Similarly, carbon monoxide being a gas cannot donate electron density using charges. Water for that matter, it's a solvent, it's a liquid. So it cannot donate electron density in the form of ions or charges. Right? Okay. Then we have chelating ligands. Chelating ligands are non-cyclic ligands. Now what do you mean by non-cyclic? Polydentate to be precise. Now what do you mean by non-cyclic? Cyclic ligands are ones which form cycles like ethylene diamine. Ethylene diamine is a ligand which is like that. Okay. So this is a cyclic ligand because it forms a cycle with the metal atom. Non-cyclic meaning which are open chain substances, right? Like EDTA. EDTA. What's the full form? Ethylene diamine tetraacetic acid or tetraacetate rather. Okay. Now, what's the structure? COO minus CH2N, CH2CH2N. This molecule repeats itself, CH2CO minus. Since it's a tetraacetate part, so it would repeat and CH2CO minus. This is the structure of EDTA. Now, this is not a cyclic kind of ligand because it's an open chain ligand, right? So, such kind of ligands are referred to as chelating ligands. Now, this is a brief introduction to the kind of ligands which we have. We will know more in detail when we learn about the nomenclature of coordination compounds, right? Okay, so where did we begin? How do we draw a coordination compound, right? So, for a coordination compound, we need a metal, a ligand, and we need to know the primary valency of the metal, which is the oxidation state of the metal. And what do we need to know? The denticity of the ligand, whether it's a monodentate or a bidentate or a neutral or a chelating ligand, right? So when all of these things are summed up, let's go back to the example that we had already taken. Was this? So here we have found out that cobalt has an oxidation state of +3, right? So how do we draw? Cobalt is the central metal because the metal is the portion or the species that will accept the electron. We have Cl minus. So Cl minus would donate its electron density like that. Now notice that I am not using single bonds or any kind of double bond in the structure. I am using arrowheads. Right? Now why am I using arrowheads? We have discussed it in the previous class. If you haven't watched it, do watch it. Because otherwise it will be difficult for you to understand what we are doing. And there I have already discussed that in coordination compounds, it is not a permanent kind of bond. It is just a mutual treaty between the ligand and the metal to somehow attain a state where both of them can stabilize themselves by mutual use of electrons. Right? But it's not a permanent bond. Another thing, you might see that here I have written NH3 and I have written H3N. Why not NH3? Reason is very simple. Since nitrogen has the lone pair which will act as a ligand. Hydrogen does not have any electron density to donate. So, writing NH3 and using an arrow like that, which I have done here, is wrong. Why? Because it shows that as if hydrogen is donating the electron density to carbon, which is not the case. It is nitrogen which is donating the electron density to carbon. So, you should not write it that way. You should actually write it as H3N so that the things become much more clear, right? So, let's just write it as H3N like that. Okay, so this is how a coordination compound is actually written on pen and paper. Let's take another example for our practice. That is AgNH3 whole to Cl. Now, this is the coordination sphere part, which is the coordination compound part, and this part is outside the coordination sphere. Right? So, what do? Cl has a charge of -1. So, in order that this whole compound becomes neutral, this coordination sphere should have a charge of +1. Right? Now, considering the charge of Ag to be x. So, x and plus ammonia being a neutral ligand is 0 should be equal to +1. So we got that silver here has a charge of +1 or a primary valency of +1. Right? Let us take an example, another example, CuCl4 and we have Na2. So sodium has +1, so 2 sodium means +2. This whole compound to be neutral, coordination sphere should be -2. So this is X. Cl is a monodentate ligand, so -4, -1 into 4, -4 equal to -2. So X here should be +2, or the oxidation state or the primary valency of cobalt is +2. Yeah. So on the basis of these things, coordination compounds were classified into 3 parts. Coordination compounds were further classified on the above observations into 3 parts. So, coordination compounds are classified into 1, 2, and 3. What are the classifications? One is cationic compounds. Second one is anionic compound. And the third one is neutral compound. Cationic means the coordination sphere, that is the one within the third bracket, should be positively charged. Anionic means the coordination sphere should be negatively charged, and neutral means there should be no charge on the coordination sphere. So, for example, CONH3 whole 3 Cl3. Now, this coordination sphere has 0 charge. Why? Because there is no kind of ions outside the coordination sphere, so that this coordination sphere attains a charge. So what do I mean? That is, the coordination sphere has no charge here. Hence, it is referred to as the neutral part. For anionic complexes, what can we write? Suppose AgNH3 whole to Cl. No, it should be the cationic one. Sorry. Suppose I'm writing Cl minus. Okay? So this Cl minus is the negative part. So in order to make the whole compound neutral, the coordination sphere should be +1. Now, since the coordination sphere gets a charge of +1, we would refer it to as cationic spheres. For anionic sphere, what can we write? Suppose this one, Na2COCl4. Each Na has +1 charge, so both the Na will make it +2 charge. In order to make the whole compound neutral, the coordination sphere should have a -2 charge. Since the coordination sphere has a negative charge, it is referred to as an anionic coordination compound or an anionic complex. Clear? Now, in the next class, we shall discuss about the nomenclature of coordination compound. But before leaving, I think one more part we need to discuss is, suppose I have this compound CONH3 6Cl3. The one within the third bracket is referred to as the coordination sphere, which we have just discussed, right? This is referred to as coordination sphere. And the one outside this coordination sphere is referred to as ionization sphere. Now, what is an ionization sphere, or what is the difference between the two? Whenever a coordination compound like that is dissolved in water or dissociated, to be precise, the coordination sphere does not break, or in simple terms, the one within the third bracket does not dissociate, does not break up into individual cobalt ion, ammonia gas, or things like that. It does not happen, right? Only the one outside the coordination sphere splits into its corresponding ions, not the one within the coordination sphere. Okay? Since the one outside the coordination sphere splits into its corresponding ions, it is referred to as the ionization sphere. Okay? And the one within the third bracket does not dissociate, and that part is referred to as the coordination sphere. Yeah. So this is basically the basic concepts of coordination chemistry, on the basis of which the entire topic will be decided. The entire topic will be taught. But first things first, if this part is not clear, then the higher parts, or the parts which are after all of this, will not be easy. Rather, it will become very monotonous and boring. So this part, this foundation part, has to be extremely clear to all of you, so as to build your concepts further. In the next class, we shall do the nomenclature of coordination compounds, which is a very important question in your board syllabus, as well as your joint entrance or any kind of competitive exams that are concerned. And then we shall move on to the depths of the topic, right? So today we shall stop here. In the next class, we shall be proceeding with the next part of the chapter. Till then, take care and stay safe. Bye-bye.